Last Friday we finished chapter 8, but since it's been spring break and a little bit of time since we've covered it, let's just do a brief review. So, chapter 8 is really about the sampling distribution. We want to answer a question about a parameter, which we can't get because we can't get all the data from the population, so instead we take a sample. And we want to know what that scatter of the estimates around the parameter looks like. So this kind of goes back to this question that we posed way back in chapter 3. And really all we're doing in chapter 8 is we're putting a finer point on this problem, and we're actually determining the exact distribution that our estimates have. And so the tool that lets us say what the sampling distribution looks like. Remember, the sampling distribution is the distribution of the estimates. So this is the distribution of our sample estimates. The thing that lets us say what that sampling distribution is the central limit theorem. Okay. And the central limit theorem is essentially a mathematical result. And even though it looks kind of complex and everything, really it's pretty simple once you break it down. So it says if you're working with a categorical variable, you're going to be trying to estimate pi. So your estimator will be pi hat. And the central limit theorem says, well, if you have a sample that's random and it's large enough, and notice here that in the sampling distribution we actually can define what large enough is, right? It says whatever the population parameter is, when you multiply it by the sample size, you have to get at least 10. And when you multiply the sample size times 1 minus the population proportion, you have to get at least 10 also. But we can't have a sample that's too large. In other words, our sample size can't exceed 10% of our population. So if all of that is true, then the central limit theorem lets us state what the distribution of pi hat is. It says pi hat has a normal distribution. It's centered around the population parameter, which again is not a surprise. We know that because the sample is random. That actually we don't need the central limit theorem for. And the standard deviation of the pi hats looks like this kind of complicated quantity here. And notice the key thing here is this n. So one of the things that we said before is when we have a sample size that's increasing, right, the estimators are going to become more precise. The spread of the estimators is going to get smaller. And we see this here. As n is increasing, the standard deviation of the estimators, which is a measure of their spread, is decreasing, just as we expected. And this tells us why. Okay, this tells us why larger samples are actually better. On the other hand, if we're working with a quantitative variable, we're trying to estimate mu. So our estimators are mu hat. And again, we have the same sort of conditions, right? We need, again, a random sample. The condition for the sample size is kind of interesting here, though, because this is an either-or situation. As long as one of these is met, we're okay. So we can either have a sample size of at least 30, or our variable can have a normal distribution. And so it's important to recall what variables that we know have a normal distribution without being told. And we recall these are deviations from manufacturer's claims. So whenever something's being produced, we assume that the deviations about the average are going to have a normal distribution. Physiological measurements. So blood pressure, height, weight, things of this nature. And finally, standardized test scores. So this includes IQ, GRE, SAT, etc., etc. And again, we have the same condition, but not too large. So these last two conditions are identical. So notice that some of the conditions are the same. Whoops. For both estimators. And in the case of the quantitative, if we satisfy these three assumptions, then we can go ahead and say that the distribution for the sample means has a normal distribution centered around mu. Again, we know that's going to be the case because we have a random sample. The estimator should be centered around the parameter. And the standard deviation looks like the standard deviation of the variable divided by the square root of n. All right, good. The one thing I want to emphasize here is that we have two different standard deviations going on here. And so sometimes people write these kind of explicitly to indicate which is which. So sometimes we want to write the standard deviation of the variable, we write the standard deviation of x. And this is what this sigma is. It's the standard deviation of the variable. The standard deviation of mu hat is this standard deviation. It's the standard deviation of the variable divided by the square root of n. And again, the same comments apply to what we said for the sample percentage. As the sample size is getting larger and larger, the standard deviation of the estimates is getting smaller and smaller, which means the estimates are getting more precise and more tightly clustered around mu. Okay, so this is what the central limit theorem is telling us about the sampling distribution. Some helpful hints when you're working on problems with the central limit theorem. First of all, use what we learned way back in chapter 2. When you start these problems, try to understand the context, which means that you want to take this problem apart, and first you want to identify what the parameter is, then the variable, and then the population. After you do that, not a bad idea to go ahead and identify all the numbers. Highlight all the numbers, identify which is the sample size, that's always going to be in there, what the value of the population parameters are, so pi or mu and sigma, okay? And finally, if you're given a sample estimate, what its value is. One of the things you're going to have to be careful about is the fact that when you're dealing with these problems, there's two percentages and there's two means. Okay? So you're going to have a population percentage, right, which is pi, and you may have in the problem a sample percentage, which is pi hat. And the same thing applies for the average or the mean, right? You're going to have a population average or a population mean, which is mu, and a sample mean, which is mu hat. And one of the things that you're going to have to be able to do is identify which is which. So if the value comes from a sample, there has to be language that suggests that. So for example, if something is a sample percentage, we should be told, or there should be language that indicates it comes from a sample. The same with a sample mean. Like we take a sample and we compute its average and find that. Okay. On the other hand, when we're dealing with population parameters, these are basically stated as given. Okay, so these do not, there should be no language suggesting this comes from a sample, and these are just stated as given. Okay. So if something is stated as a fact, it's generally going to be a population parameter. All right. When you're applying the central limit theorem, again, make sure your conditions are satisfied. We're going to learn how to create Excel templates so you can do these calculations expeditiously and with as little error as possible. And I'll show you guys how to set that up. And all of our calculations we're going to do in Excel. We're not going to do anything by computer or by hand. So one thing I want to do before we move on and work problems is I just want to go back to this male rat empathy problem and just kind of illustrate how this all ties together. So we asked this question, are male rats empathetic? And recalling that statistical questions are always questions about parameters. We defined this parameter pi, which is the percentage of rats that would open the door to let a caged rat out. And we defined empathetic as being when the percentage of male rats in the population who would open the door is greater than 50%. So we morphed this kind of vague question into a specific statistical question. And the way that we try to show that in statistics is we try to show that it's too unlikely that it could be 50%. And then basically if it's too unlikely that it could be 50%, the only alternative is that it has to be greater than. All right. So if you kind of think about it for a second, here's 50%. And there's basically two options. The first option is the hypothesis that we're trying to prove. So this is what we're trying to prove. And the alternative to this hypothesis is that it's 50 or less. And basically, if I can show that it's not 50, or I can show it's too unlikely that it's 50%, then I've shown that it's too unlikely it can be 50% or less. And this only leaves one other alternative, which is that it has to be greater than 50%. This is the logic behind this. So in our study, we had 24 male rats, 17 did open the door, 7 didn't, and so our sample percentage of male rats that opened the door was 70.8%. And so the first question we want to ask is, what is the sampling distribution for pi hat if we were taking random samples of size 24? In other words, what do we know about this distribution of pi hat? And we want to use the central limit theorem. So first, let's make sure that the assumptions are satisfied, okay? So we assumed that we had a random sample. So let's just check our assumptions. So we assumed that it was random. And we want to check to see if it was large enough, right? So our sample size was 24. And pi was 50%. So that's 12, which is greater than or equal to 10. And if we look at n times 1 minus pi, we're going to get the same thing, right? So our sample's large enough. And it's not too large. I mean, 24 is not 1/10 of the entire population of all male rats. So it's not too large. So all of our assumptions are satisfied. We can use the central limit theorem. So in this case, we're assuming that pi is 50%. So this tells us that by the central limit theorem, that pi hat has a normal distribution. It's centered about pi, which is 0.5, and the standard deviation is pi times 1 minus pi divided by 24 square root. And if you go ahead and you do that calculation, you're going to get 0.5 divided by the square root, which is roughly, it's going to be roughly 0.1. It'll be a little bit more. Let's go ahead and calculate it really quickly here. Let's see. And sure enough, it's a little bit greater than 1. It's it's a little bit greater than 0.1. It's 0.102. So we can say that this has a normal distribution of mean of 0.5 and a standard deviation of 0.102. which we could also express as a percentage, right? It's important to understand that when you're doing the calculations in Excel, you're always going to have to use decimals though, okay? So the way that we're going, so in chapter 9, the way we're going to actually answer this question is we're going to ask, well, how likely is it that if the opposite of our hypothesis was true, okay, if it was really less than or equal to 50%, we could get a sample percentage of 70.8%. So if pi was equal to 50%, we just showed that this is what the distribution of pi hats should have to be. So this is the mean, 50%. I'm going to step out on units of standard deviation. I'm not going to worry about the 0.2 for right now, okay? We could put this into Excel, but I just want to kind of show you what's going on with the calculation. So this is the sampling distribution for the sample percentages. And notice that we aren't surprised. We kind of suspected that because of the small sample there was going to be a lot of spread. So how likely is it that we could get 70.8%? We want to remember how likely is the same as percentile. So I want to compute the percentile of 70.8%, and in fact I want the upper percentile. And I can actually tell by the empirical rule what this answer is going to be. I can estimate it quite accurately. I'm not, even though I'm dropping this 0.2, it's not going to have a great deal of effect, right? So 2 standard deviations away is 95%, right? 5% in the tails, 2.5% in each tail, so there's going to be roughly about 2.5%. And if I wanted to get the exact number, what would I do? Well, I would use norm.inv, right? I'm sorry, I would use norm.dist, right? So I would say norm.dist 70.8, 50, 10.2, true, and get my answer. And let's go ahead and do that. Okay, let's see, make sure this isn't a figment of my crazed imagination. So if I do this calculation, and we're going to set up a template soon. Okay, I'm just going to do a really quick calculation just for the time being. Okay, so we'll say norm.dist 70.8%, 50, and true. And I'm going to have to use 1 minus, right? Because remember what norm.dist does, it gives the area in the lower tail, right? And I want the upper tail. And I'm going to multiply it by 100 also. And you can see, sure enough, I get around 2.5. I get 2 point something, okay? And here's the command. Here I'm going to copy and paste this so you can check both the number and make sure you're entering the command correctly. Okay. And this is how we make decisions with statistics. We're going to say if this result is too unlikely, and we're going to generally consider 5% as too unlikely, there's less than a 5% chance we could have got this value, then we're going to reject the fact that this is the correct distribution, which means that we're going to reject the fact that we believe pi is really equal to 50%. And this is where we're going actually in chapter 9 next.